All right, let's talk about a fundamental puzzle in math that, believe it or not, shows up all over the place, from figuring out lottery odds to writing software. We're going to get to the heart of how we count things. Specifically, we're looking at the difference between counting arrangements versus counting groups. Now, that might sound like a tiny detail, but as you're about to see, that difference is, well, it's everything.
So, to really get what I'm talking about, let's start with a simple scenario. Picture this. You've got 10 people. In one case, you need to hand out gold, silver, and bronze medals. In another, you just need to pick a 3-person team. Now, your gut probably tells you those are different problems, right? But why? The number of possible outcomes is wildly different for each, and the reason for that is exactly what we're going to unlock today.
Let's tackle that first problem, the race. This brings us to our first huge idea, permutations. Think of this as the tool you grab anytime the sequence, the arrangement, or the order itself is what really matters.
So what exactly is a permutation? Well, it's an arrangement of a certain number of items, which we call R, that you're picking from a bigger group of items, which we call N. And the number one rule here is that order matters. Now, that formula might look a little intense with those exclamation points. Those are called factorials. All a factorial means, like 5 factorial, is you multiply that number by every whole number below it. So 5 times 4 times 3 times 2 times 1. It's really just a handy shortcut for a long multiplication.
Okay, let's use this on our race example. Our total group, our N, is 10 runners, and we're choosing for 3 places, so R is 3. First, we have to ask the big question, does the order matter? Oh, you bet it does. Finishing first is definitely not the same as finishing third, so we know to use the permutation formula. As you can see, that's 10 factorial divided by 7 factorial, which simplifies really nicely to just 10 times 9 times 8, and that gives us 720 possible ways to award those medals.
So, what about forming that team? This is a completely different kind of problem. In this case, we couldn't care less about the order people are picked in. All that matters is the final group. And for that, we need our second big idea, combinations.
A combination is just a selection where the order is totally irrelevant. You know, like a hand of cards, a toppings on a pizza, a project team. It doesn't matter what order you get them in. Now look closely at that formula. You see that extra R factorial on the bottom? That's the secret sauce. Its whole job is to divide out all those duplicate arrangements that a permutation would have counted. This makes sure we only count each unique group one time.
Okay, so how do you decide which one to use? Honestly, it all boils down to this one single powerful question. Does changing the order create a different outcome? If the answer is yes, like a password or a race finish, you need a permutation. If the answer is no, like a committee or a lottery ticket, you need a combination. Seriously, this question is your secret weapon for solving these problems.
Let's put that key question to the test. Imagine we're choosing 4 committee members from our 10 people. So N is 10, R is 4. Does changing the order create a new committee? Nope. A team with Alice, Bob, and Carol is the exact same team as a team with Carol, Bob, and Alice. The outcome is identical. That big no is our signal to use the combination formula. When we plug in the numbers and calculate it out, we find there are 210 unique committees.
You know, that huge difference between 720 ways to award medals and only 210 ways to form a committee really says it all. This side-by-side comparison makes it super clear. Permutations are for arranging, for lining things up, for anything where order is king. Combinations are for selecting, for choosing, for groups where it's not. If you look for these keywords in a problem statement, they'll point you to the right formula almost every time.
Okay, so you've got the basics down, but really mastering this means knowing where the common traps are. Let's take a quick look at a few pitfalls that people often stumble into when they're working on these kinds of problems.
The biggest mistake, and it's not even close, is using a permutation for something like a team where the order just doesn't matter. You always have to go back to that key question. Another little tricky spot is forgetting that 0 factorial actually equals 1. It's kind of weird, I know, but it's a rule that's crucial for making the formulas work sometimes. And finally, when a problem says you need one thing and another thing, remember to multiply the possibilities, don't add them up.
Let's see that "and" rule in action right now. Imagine we need a committee with exactly 2 women from a group of 4 and 1 man from a group of 5. The trick is to break it into 2 smaller, separate combination problems. First, how many ways can we choose the women? Well, that's C4, 2, which gives us 6. Second, the ways to choose the man.
That's C5, 1, which is 5. And since we need the women times the man, we multiply those results. 6 times 5 gives us 30 total possible committees.
So you might be thinking, this is neat math stuff, but is it just for textbooks? Absolutely not. Understanding this code of counting has massive real-world impact, especially when it comes to understanding probability and, well, your actual chances of something happening.
Let's take the lottery. It's a perfect example. In a typical 649 game, you choose 6 numbers out of 49. So let's ask our key question. Does the order you pick the numbers in matter? Of course not. As long as your ticket has the winning numbers on it, you win. That loud and clear no tells us this is a classic combination problem. Our job is to figure out just how many unique combinations of 6 numbers can possibly be made from that pool of 49.
And the answer? It's almost 14 million. Yeah, let that sink in for a second. There are nearly 14 million unique 6-number combinations you can make from just 49 numbers. Suddenly, the odds of winning the lottery look a little different when you see the actual math laid out, don't they? This is the power of combinations on a huge scale.
So if you only take one thing away from all this, let it be this. It all comes down to that one simple question. Knowing whether or not order matters is the key that unlocks the whole problem. It turns what seems like a confusing counting mess into a straightforward calculation where you just have to pick the right tool for the job.
And that leaves us with a final thought to take with you. Just think about your day. Is picking out an outfit from your closet a permutation or a combination? What about the tasks on your to-do list or the route you take to work? Once you start asking that key question, you'll start to see this hidden mathematical code absolutely everywhere.